In section 4.2, we still look at finding probability, but now we look at compound events using addition rules. So that'll be our focus, which more or less we did talk about addition rules kind of indirectly in the previous section, but now we more define those addition rules and talk about some different components that you want to look out for when we have events, compound events that apply to using the addition rules. So the first thing that we look at here is what a mutually exclusive means, or disjoint events. So if we have two events, they're mutually exclusive if their events have no outcomes in common. If the events have an outcome in common, then we consider those events not mutually exclusive. So for this example, to kind of talk about mutually exclusive events, I have this problem about the US population, and then I'm going to draw a Venn diagram to kind of illustrate the mutually exclusive part and the not mutually exclusive part, and then we'll calculate some probability. So the US population says the data show the US population by age. So if we chose one person from the US at random, we want to find these different probabilities. So over here in this table, we have age groups and we have percentages. And these are our three different kind of events we can look at. Event A is that the people who are under the age of 20, which is 27% of the population. Event B are people who are 20 years or older, which is 73% of the population. And event C, 65 years or older, which is 13.1% of the population. If we were to add those together, then we get more than 100%. So that is an indication of an issue where we don't have mutually exclusive events. So there must be something in common here, because it's greater than 100%. It's not possible for us to have 113% of the people represented in that table. So there clearly is some overlap here, and that overlap will be for events B and C, because event B is 20 years older and event C is 65 years and older. So these 65 years and older individuals are included in event B as well. So to illustrate that kind of visually for you, I'm going to make a Venn diagram to kind of show this. So first we have event A. Event A has no overlap with any of the other two events. So we can safely say that that 27% is all contained here in this kind of this first circle. That represents anyone who is under the age of 20 years old. And then we have two other events that are related to each other, which is events B and event C. So event B in kind of this red circle represents anyone who is 20 years and over, and event C represents anyone who is 65 years and older. So we already know that in this red circle, there's a total of 73% of the population. But in that total also includes 13.1% of anyone who is 65 years and older. So when we break down event B, part of that 73% is included within event C. So we simply, if we subtract these two numbers, then that will tell us the individuals who are in event B only, but not in event C. So mainly the percent of the population who's 20 years old to 64 years old, pretty much. So if we subtract that, we get 59.9% of the adults would be 20 years or older until you get to 64, and then 13.1% of the adults are 65 and older. Now there is no number in this part, because this 13.1% is shared between group B and group C, and then total in group B, if we put those two numbers back together, is a 73%. So if we compare event A to event B, those are mutually exclusive because they have nothing in common. If I compare group A to group C, those are mutually exclusive. They have nothing in common. But Group B and Group C are not mutually exclusive because they have information in common. So they would be not disjoint events. So now we can look at how we calculate probability. It says choose one person at random, find the probability that the person is from 20 years old to 64 years old. Well, we can get that information directly from our Venn diagram. That's the 0.599. That will be these individuals here, or we could have also gotten it from this table, but I wanted to give you kind of an illustration of what mutually exclusive or disjoint what disjoint events look like. So that would be the 0.599. About 60% of the population is between 20 to 64 years old. So for the second one, it says under 20 or 65 or older. Well, we can look at anyone who's less than 20. That's going to be here, 27%. Anyone who's 65 or older is going to be the 13.1%. So we kind of combine those together, and that's about a 40% chance. So if you are not 65 years or older, then we can definitely use here a complementary event, right? We don't really have to, but we certainly could use a complementary event here. So anyone who is not 65 years or older, that's the probability of the entire population minus someone who is over 65 years old. So 1 minus that 0.13 is 0.869, which is very likely to occur, right? If we selected an individual at random, if we selected an individual at random, then there's about an 87% chance that they're not over the age of 65. So we'll kind of continue. This is where we can kind of formalize what the addition rule is. We've mainly been using it in 4.1, and even in the previous example, anytime we see the word or, I've been adding the numbers together. I just haven't really said that yet. So this is where we can kind of formalize what the addition rule tells us. So for that example, now we're back to probability with cards. So I provided the sample space again because I didn't want to write out those 52 items. So if we select a card, if one card is drawn at random from an ordinary deck, find the probability of getting the following. So if we want the probability of us getting a king or a queen or a jack, well, we have to look at, for a king, we already know from 4.1 that there's 4 kings in the deck, so 4 out of 52. And then a queen, 4 out of 52, and then a jack, 4 out of 52. So this event is actually mutually exclusive, right? This event, they have no outcomes in common. So we can easily look at the probabilities, and we don't have to worry about, or because they're mutually exclusive, I don't have to worry about any overlapping outcomes. And so the addition rule tells us that anytime we have a probability that involves the word or, we simply add those probabilities together, which is what we've already been doing. Or means any part of that event can occur. So the word or increases the likeliness of that event happening. If I reach into the deck, I can get any one of 12 cards. It can be those 4 kings, it can be the 4 queens, or it can be the 4 jacks. So that word or is increasing the likeliness of the event occurring. But we already know from before that 4 out of the 52 are jacks, 4 out of the 52 are kings, 4 out of the 52 are queens, and 4 out of the 52 are jacks, and we just add all those together, and that will give us our probability, which is a 3 out of 13 chance. And if you say there's a 3 out of 13 chance of someone, they may look at you like, what are you talking about? So we generally like to convert these into a decimal approximation, although your homework, it may ask you for either, so just be aware of how to do both. So 0.23, which again is an unlikely event. And your homework is not going to have you describe the event, but on your test for the unit, you'll describe the likeliness of the event for a few of the questions. So I want to keep reiterating that each time. So for this example, we look at a king and a queen, a king or a queen, or a diamond. So now we look at the diamonds and we notice there's some overlap, right? There's 4 kings, there's 4 queens, and there's 13 diamonds. 2 of those diamonds are a king and a queen, and they're included with the king or the queen. So these events are not mutually exclusive. Because they're not mutually exclusive, we actually have to do something with the probabilities because it's going to be counted twice. So when I look at finding the probability of a king, the 4 out of 52, that includes also a diamond. When I look at finding the probability of a queen, the 4 out of 52, that also includes a diamond. When I find the probability of a diamond, the 13 out of 52, that includes a king and a queen. So when events are not mutually exclusive, such as this one, we have to subtract out whatever they have in common because it's being counted more than once. In this case, it's being counted twice. The probability of a king, one of the kings is a diamond, one of the diamonds is a king. Probability of a queen, one of the queens is a diamond, one of the diamonds is a queen. So I have to subtract out where they overlap. So the probability of a queen of diamonds, 1 out of 52, and the probability of a king of diamonds, 1 out of 52, and we subtract those out. And that will give us our resulting probability, which is 19 out of 52, 0.365, so that's somewhat unlikely to occur, right? It's definitely higher than unlikely, but it's lower than equally likely, so it's somewhat unlikely to occur. Now, we continue to try to look and determine if events are mutually exclusive or non-mutually exclusive, and this is all addition because we only see the word or, a sum of 8, 9, or 10, doubles, or a sum of 7, a sum greater than 9 or less than 4. So we think about our first probability. So we roll 2 dice. This is the sample space, these 36 outcomes. We want to find the probability of getting a sum of 8, 9, or 10. So we have to think about, is there a way to roll the 2 dice and get a sum of 8, but also at the same time get a sum of 9, or at the same time get a sum of 10? And there's not. So this would be mutually exclusive because there is no outcome in common. So we go through, look at our sample space, and we find everywhere where the sum is an 8, and that represents these 5 outcomes, 5 out of 36. And then we look everywhere it was a 9, and that's these 4 outcomes. And everywhere that it is a 10, and that's these 3 outcomes. And because we can get either of those outcomes, it can be an 8, or it can be a 9, or it can be a 10, that increases the likeliness of the probability or the chance of that happening, so we add them together. And so overall, there's 12 outcomes where the sum was 8 or 9 or 10 out of 36, so there's a 33% chance of that occurring. So for our next kind of 2 examples, if we look at doubles or a sum of 7, or for me to get doubles, that means they'd have to be the same face value. And so if I add those together, it's always going to be an even number. 1 plus 1 is 2, 2 plus 2 is 4, 3 plus 3 is 6. So a sum of 7 would be an odd number and an even number. So mutually exclusive again, right there, no outcomes in common. And if I look at the next one, a sum greater than 9 or less than 4, well, there's no way that I can add 2 numbers together and get 9, and those same 2 numbers give me 4. So this would be mutually exclusive as well. And then we would just find the probability like we did before. Look at the sample space, figure out where are the outcomes necessary to calculate that probability. So for doubles, it's all of these 6 outcomes out of the 36. And then for a sum of 7, it's all of these, again, 6 outcomes. So 12 out of the 36 outcomes would be doubles or a sum of 7. So similar to the one before, a 33% chance.